Hello, this is chapter 14, the second problem. Okay. So once again, it's testing to see whether something fits someone's idea. So what's the idea? That equal numbers of children would be born in each season. So how many seasons are there? 4 seasons, right? And so if there are 120 students in a class, then what's a fourth of 120? 30. So let me open Excel. Okay, so the expected number of children in each season is a quarter of the 120 students. So it'd be 30, 30, 30, 30. The observed number of children is 28, 36, 32, and 24. And as you know, the chi-square statistic, or the chi-square value, is computed by doing observed minus expected parentheses squared divided by expected. And you do the same formula for all the numbers and then you add those numbers up. So there we go. 2.66, etc. And how many degrees of freedom are there? There's 4 categories, so there should be 3 degrees of freedom. I forgot about that. So the expected, or the average chi-square value is the same as the degrees of freedom. And so now it's asking us for the computed chi-square statistic. It's 2.6, so I guess I did all that work for nothing. The computed chi-square statistic for the given data is 2.667. Does this seem large in comparison to the mean in part A? No, it doesn't seem very large, because in fact it's actually a little bit smaller than the average value. So even when children are born equally among all seasons, there will be some samples that will fluctuate a little bit just from natural causes. And so it's perfectly normal to have 28 born in winter, 36 in spring, 32 in the summer, 24 in the fall, even if the average amount is really 30, 30, 30, and 30. Okay, now the null hypothesis is that this is called the goodness of fit test. So the null hypothesis is that the supposed distribution of data is actually valid. So the equal numbers of children in each season. So that would be births are distributed uniformly across the seasons. So it could be A or D. The alternative is that that's not true. And if that's not true, it could be true in 1 or 2 cases. It doesn't necessarily have to be not true in all the cases. So A would be wrong and D would be the best choice. What does the comparison in part B say about the null hypothesis? So since the test statistic is very small, in fact it's actually less than the mean, there is very little evidence at all that the births are not distributed uniformly across the seasons. Okay, now let's find the critical value for the chi-square distribution with the appropriate number of degrees of freedom. So to do this, we're going to have to use StatCrunch or a chi-square table, either one. So let's see. Stats, calculators, chi-square. And it's going to be standard, and it has 4 seasons, so there's 4 minus 1 is 3 degrees of freedom. And I want to find the probability that it's greater than something is equal to 0.05. And the value I get is 7.814. 7.81 rounds off to 7.815. Excellent. Using the critical value, what do you conclude about the null hypothesis? So the test statistic of 2.667 is definitely a lot less than the critical value, and so we will not reject the null hypothesis, which means there is not enough or insufficient evidence that the births are distributed. Excellent.